This video is about sideband noise in oscillators. The particular issue is the relation between amplitude noise and phase noise. And this is something that I wanted to look at after having seen the properties of this particular oscillator from CTI. It is rather special. I have a setup where I collect the phase noise rapidly. The yellow trace here is the phase noise up to about 7 kHz. It is around minus 150 dBc per hertz. And the statistics is already very good after 30 seconds. I can look at the amplitude noise. It is here. And it is also very good statistics at the same short time. The imaginary part is far below the real part. So this is the amplitude noise at minus 143 dBc per hertz. And I can click again in this box. The white track, amplitude noise. The yellow track, phase noise. And up here there is a new feature in Linrad. Up here is the correlation between phase noise and amplitude noise. The white track is the real part. It means that there is no correlation in phase between the amplitude and the phase modulation. But there is a significant correlation between amplitude and phase modulation when they are shifted 90 degrees with respect to each other. And the scale is 0 at the red track in the middle. 1 means identical. And minus 1 here means identical in one phase. And 1 here is 180 degrees opposite. I don't remember which, if it is 90 or 270 degrees down here, corresponding to the 1. When the modulation is the same in amplitude and in phase, it means that the sidebands are correlated. So it means here that the correlated part sums in phase here and in antiphase here. And it is a small difference, but it is clearly visible. I have added an amplitude limiter like this. First amplify a bit and then crossed 1N, 1N, 41, 48. And then a series resonant filter. It is not tuned exactly on the resonance, it's tuned a little bit off because that optimizes the performance. And here is what I see. The amplitude noise is much weaker. And the phase noise is also a little bit weaker. There are two outputs on the unit, one here for sine waves and the other for TTL. I will put a short on the sine wave output here. This seems to improve a little bit more, but the amplitude noise is very noisy, and therefore the correlation curves also become noisy. If I click here to look at the phase noise, it looks very good. The imaginary part is well below the real part. But for amplitude noise, the signal to noise level is not good enough. The imaginary part reflects the statistic noise, and below 2 kHz I don't have a reliable reading. And here at 7 kHz I would have to wait some more time to get a flat trace. But that's not really important. What I can see is that the remaining amplitude noise is very strongly correlated with the phase noise. So something could be done taking the information from the amplitude noise and use that to produce a phase modulation that would cancel the phase modulation. So if this is a general way to fix oscillators, it would be very important to know. That's why I had added the routines to provide the correlation between amplitude and phase modulation, which you see here. And I didn't provide a scale and other things for it. I just was curious to see whether this phenomenon exists in other oscillators. This is a significantly better oscillator, at least when it comes to wide-range sideband noise. I have looked at it with the correlation mode 1 in Linrad, and the number of averages is 4,400 for the green and 500 for the yellow. And you can see the green trace is much narrower than the yellow here. And of course the white is the spectra without any correlation. At wide range, above, let's say 4 kHz, amplitude noise and phase noise are close to identical. And they are not correlated, or very weakly. It seems that the yellow trace is a little bit below the white trace, and the white trace seems to be on the red line. So it means that the correlation that is there is at 90 degrees, but it is so small so it cannot be used to reduce the phase noise. So at wide range there is nothing to do using the AM modulation. At close range there are artifacts. You can see the lines in the red in the imaginary part. That is not from the signal source, it is somehow from the SDR IP units. I have set it to 10.0 MHz. I can change that a little bit. 10 kHz. So I have to move to 10 kHz here. And it looks very much the same. But it is phase noise, not amplitude noise. And the correlation, I don't know what to do about that. It doesn't seem meaningful. This is an even better oscillator from Wenzel Associates. It is supposed to be -166 dBc per Hertz at 10 kHz, or 165 at 1 kHz. That's not quite what I'm seeing. It looks more like -171, but it will take a long time before I have a flat line, because signal to noise ratio isn't very good with the current system that I have. And when I look at the amplitude noise, it is well below what I can see after only 4 minutes or 5 minutes. 4:58. Yeah. So the correlation between amplitude and phase modulation will be noise only, because the AM is noise. So even if the phase modulation has some reasonably accuracy on its phase and amplitude, it cannot be correlated to the noise in the amplitude modulation channel. So whether there is a correlation or not, I cannot say now. Maybe tomorrow, because now it's late in the evening. This was a too difficult task for Linrad in the current setup. After 3 hours and 45 minutes. It has stopped working because the third FFT buffer is full. I don't know exactly why, but I know that the baseband workload has been very high, and if it hasn't the capacity to remove data from the third FFT buffer, this is the error to expect. And within this time, 3 hours 45 minutes, I don't see anything of the amplitude noise. I just see noise. So this oscillator is too good, and there will not be any possibility to use the amplitude noise to correct the phase noise because it's so low. I have reduced the transform size from 12 to 9 to make the collection of averages faster, at the expense, of course, of a much lower resolution. So maybe I will be able to see the amplitude noise now. But the load on the baseband processing thread is very high, so I allow Linrod to show the timing. It says 70% for a single core, and that could be risky if the computer decides to do something that takes a little extra time. This does not work properly either. You can see that the total delay here is 12,000 seconds. So data is accumulating in the buffers and things will fail fairly soon, I think. And the data is piling up in the baseband buffer. So it means that this procedure doesn't swallow data fast enough, even though I changed the transform size from 9 to 10. Now, it has been running long enough for the real part to dominate in the average transform for the amplitude modulation. So I can look here, and it's clear the AM noise is falling rapidly like this, and it is in the order of minus 180 dBc per hertz. But I can see here that the amplitude and the phase noise, they are not correlated at large frequency offsets. What happens here in the close range, I'm not so sure I can trust after having set the parameters I'm using now. This can be better studied with the sound card than with the SDR eyepiece. I have connected the 10 MHz reference oscillator inside this unit. The sideband noise level is very high. It is the same as the noise level of the system. Means the noise of the SDR IP is not visible here. And this is phase noise. Amplitude noise is the same. So the signal to noise ratio of the modulation is very good. And this means that I can see the correlation here as very stable noise-free traces. There is a correlation at low frequencies up to about 3 kHz. There something happens. There is a filter involved somehow. And we can see, of course, also that the amplitude modulation varies like this. And the phase modulation has a similar behavior. Although it seems to be phase shifted, it has a maximum here, close to where the AM modulation has a minimum. Well, not quite, because here is a maximum and also there is a maximum. Anyway, at higher offsets the correlation is very small, and it is the same in the real part and the imaginary part. It means that this is something like 45 degrees between the two modulations. But it's insignificant. It is not useful for any purpose. I am now using this oscillator again, but I have added with a combiner the noise from a couple of series connected amplifiers having a dummy load at the input. So there is a high noise level added to the signal from this. And the spectrum looks like this, and the waterfall indicates there is a lot of noise. And here is the modulation. The sideband noise is at minus 134. The correlation between AM noise and phase noise is 0, fairly accurately. And I have seen this in 20 seconds only, because the noise is high above the internal noise of the system. This is just to verify that things are doing what they are intended to do. And also to see that at very low frequencies there are artifacts because of the settings I'm using. I have a very high baseband sampling speed, and it doesn't work right for low frequencies. I have now set a very large transform size, 17 here, and that is to be able to look at relatively close range despite the very high baseband sampling speed I have. It is still the Wenzel oscillator, this one, with added white noise from a chain of amplifiers. And at 150 Hz you can see the noise is here. The imaginary part is far below. So down to about here the measurement is okay. But at this point the imaginary part starts to grow. That is a signal that shouldn't be there. It is in 90 degrees with respect to the common noise between the two channels. So this is an artifact of the hardware. And there are spurs, that's not really a problem. But here there is something added in phase, and the imaginary part is almost equally strong. So down to maybe 50 Hz, this is a reasonably reliable result. Looking at the amplitude noise, it looks much better. For some reason, the distance between the imaginary part and the uncorrelated spectrum stays constant all the way up to here. Almost, at least. So this is not a problem. And here you can see amplitude noise and phase noise are the same. Although at 30 Hz or so the phase noise start to be noisy. But down here at 10 Hz it's no longer okay. And not surprising, because this baseband filter is about 10 Hz wide. Correlation, there is no correlation. You cannot see the red line, you can see it here. It's exactly 0. But down here there are peculiarities, but they are not significant, I think. I need something else to understand what that might be, if there really is something there. I have switched from the SDR IP to a sound card, M-Track Quad, which is modified for this purpose. And you can see the noise that I am adding, it's the same as the previous with the SDR IP. It's added to the signal from the Wenzel oscillator. It is an interesting and not so pleasant thing to see that the noise drops below the true value. The noise floor I added is truly white noise. It should be flat everywhere. So what happens here is a negative contribution in the real part. And it's caused by the zero frequency, DC, in the sound card. It gives 1 over F noise here. And together with the second harmonic, which is here, the audio side second harmonic. This is the signal, second, third, and so forth. So these two together give a contribution with the negative side. And I have seen that before and drawn the conclusion that this is not useful at frequencies above about 5 Hertz. And that is about here. And I have no strong reason to change that judgment. But I can do measurements at somewhat higher frequencies, but not down to the level required for the good sound cards. The imaginary part is at about minus 155, and I would need it to go down to 165 or so. And that would take too much time and probably not be reliable. The amplitude noise looks very similar. And here I have the correlation between amplitude noise and phase noise. And it isn't quite zero as it should be. There is a small difference here. The real part is zero, but the imaginary part is not quite. And of course, I don't know what is behind this. It's the same setup, but I have reduced the amount of noise that I'm adding. I simply removed one of the series connected amplifiers to reduce the flat noise floor that I'm adding to the Wenzel oscillator. And I will wait again to see what happens with the phenomenon here at close range. The noise very close here has not changed. Of course, I just removed the flat noise floor. The interference here is probably because a connector needs cleaning. This is a very difficult thing. They have to be cleaned every time I disconnect and connect back. But I'm not doing that always, and sometimes it works anyway. Sometimes I have a problem like this. What you see here is just I happen to touch something. Now, in the collection of averages, Lindblad rejects things that are occasional bursts of noise. So it shouldn't degrade the measurement I'm doing. Sometimes that fails, but I didn't see any problem this time. With the added white noise floor at minus 151 dBc per Hertz, as I have now, I can see that I can trust this measurement only from about 50 Hertz and larger separations. And here something is unreliable. The imaginary part is equally strong as the real part. Means that the phase angle is not quite the same as before, the previous measurement. And I think the phase angle that comes here depends on how well centered the signal is in the filter. Because the carrier, the phase of the carrier will change a little bit depending on where in the filter the carrier is, while the second harmonic will not change phase when the frequency is shifted a little bit. So the relative phase between the fundamental here and the second harmonic here will change a little bit, and that will change the phase relation seen here, probably. And actually it isn't very interesting, it's just I have to avoid this range. Now looking at the amplitude, it looks like this, very similar. Of course the white noise is the same, but this region has its problem, and you can see the imaginary part going up even a little bit stronger than the real part. And this is no surprise. Below about 50 Hertz, this is meaningless. At very low frequencies, this has some meaning. I will expand the spectrum to see what to say about that. It's clear that at very low frequencies, there is no correlation. That's the range where the noise from the oscillator dominates. Going a little bit above, up to 5 Hertz, there is a correlated signal. It means it is leakage from the strong correlated signal up here somewhere outside. So this tells me that perhaps 5 Hertz is a too generous limit, because here is already a contribution from a undesired and false signal. But up to 0.2 or 0.3 Hertz, the accuracy is probably good enough, at least at normal noise levels at close range. I have connected this oscillator again, and as you can see here, it is much more noisy than the situation before with the Wenzel oscillator plus minus 151 dBc of white noise. So you can see here the noise close to the carrier is pretty strong. And it means up to about 50 Hertz there is a strong noise both in amplitude and phase. But the correlated noise that was important at larger offsets, it starts to come up here at something like 200 Hertz. Here there is some correlated, and it's the same way the correlation between amplitude modulation and phase modulation is yellow. It's 90 degrees out of phase. But this is the only oscillator I have seen having this property, so the possibility to do something about it by detecting the amplitude modulation and do corrections by adding the appropriate modulation in antiphase, that is not the appropriate strategy. Just choose some other oscillator if you need a low noise at large separations. Or maybe modify the unit, because I suspect that the reason for this problem is the filter, using capacitors, ceramic capacitors that are likely noisy. So one could simply remove that filter and solve the problem. Maybe. I don't want to destroy the oscillator. I don't have the appropriate tools to work with these miniature components. Here is what I see at close range. At 1 Hertz, I see minus 104 dBc per Hertz. I have seen a little better than that on the SDR-IP some time ago. I will reset and check, because I started it when it was not really warm. As you can see, the correlation spectra and the uncorrelated spectra are very similar. And this is the average of 6 and 8. And the imaginary part is well below So what I'm seeing is minus 106 dBc per hertz. In 1 minute, the statistics is good enough. I have increased the transform size by a factor of 4. And I think that will make the noise a little bit lower here, because it is steeping fairly rapidly. So when the peak is wide, it will contain more from the low side than from the high side. We will see. This particular third spectrum added a lot of noise near 1 hertz, but this is slow, but within a couple of minutes it will be clear. Well, it still looks like minus 106 after 20 averages. So improved resolution wasn't really important. I have been measuring on the TTL output now. I think I had a different value on the sine wave output, minus 108. I will check that. So now I'm looking at the sine wave output. The level there is significantly higher, something like 3 decibels. And I set the Fourier transform size to 15, a compromise between the previous values. So it pretty rapidly will converge to a result somewhere around, it looks like minus 105 now. After a restart and a couple of hours, I see, as expected, that the 1 hertz sideband phase noise is minus 108 dBc per hertz, just as expected from previous measurements. And here is the amplitude noise. It is much lower, minus 120 at 1 hertz. And as expected, at very low offsets, half an hertz up to 1 hertz, the correlation is very small, while it is growing slowly with increasing offsets. Here again it is clear that the correlation is growing as the offset is increasing. And this is the only oscillator where I have seen this kind of phenomenon. And I don't regard it as particularly interesting. I have removed the C14 capacitor from here. It is the capacitor that couples the TTL output to a filter which provides the sine wave output. That is a small ceramic capacitor, and the filter also contains small ceramic capacitors, and they are noisy. So I have now disconnected them, and the result is very visible here. This was when it was in place. Here it is removed. Here is when I touched the board. The signal level has increased by 2.5 decibel. And the noise level is much smaller, and I have to reset the collection of data and not touch the board while collecting spectra. Here is the close range result from 1 hertz up to 7.5 hertz approximately. Before I removed that capacitor, this is what I could see. At 1 hertz, exactly on the red line, and now exactly the same. But at 7.5 hertz, It's here, minus 125, but now it is at here, minus 138. Sorry, minus 130 for the phase noise, 138 for the amplitude noise, which was at minus 125 before. Already at a modest separation like 7 Hz, there is a significant improvement in the phase noise. The correlation between the two noise modulations seems to grow with frequency. Whether that is a real phenomenon or something related to the sound cards, I really don't know. And here is what I see now without the capacitor, up to 250 Hz with the sound card. Before I remove the capacitor, this is the result. And you can see there is a big difference. Amplitude and phase were here at the arrow. That is minus 140. And minus 140 comes about here. So now it is 5 dB improvement in the phase noise and 10 decibels on the amplitude noise. The correlation looks identical. Whether that is real or whether it is an artifact of some kind, I don't know. I will have to do some other investigation to find out. Now I'm using the SDR-IP units, and of course the phase noise at 1 Hz is still minus 108 dBc per Hertz. And the signal-to-noise ratio for the measurement, as the distance between the phase noise, real part, and imaginary part is very large, 30 decibels. The close-range amplitude noise at 1 Hz is much lower, around minus 130. But it is not measured accurately. The imaginary part is only a couple of dB below. At very low frequency offsets, 1 Hz, there is no correlation between the two modulation types. It seems to increase up at 8 Hz, but it's a little bit uncertain due to the poor signal-to-noise ratio, which we can see as the signal becoming noisy here. With this configuration of the SDR-IP and Linrod, I can see up to 450 Hz. The phase noise at 400 Hz offset is something like minus 148.5. The amplitude noise, also at 400 Hz, is very similar, 149 approximately. And the signal-to-noise ratio out here is reasonably good. The noise amplitude reciprocal mixing noise of the SDR-IP units is not as high at this offset as it is very close to the carrier. And this is intriguing. Even though the amplitude noise is very low, it has a significant correlation with the phase noise. Already at an offset of 50 Hz. And in here, below 50 Hz, the signal-to-noise ratio is poor. So correlation is noisy. I have changed the settings so I can see the wide range noise rapidly. And you can see now, after 15 seconds, I already have a pretty accurate measurement. I can see the amplitude noise is growing with frequency, while the phase noise is decreasing slowly. The correlation seems to be greatest at about 2 kHz, but it's still significant at the top frequency, 7.5 kilohertz. I have added the amplitude limiter and tune it for minimum noise at 7 kilohertz offset. Minimum phase noise. It's the yellow trace here. And now it is minus 155. Without this limiter, I had it like this. It was minus 152. A little bit above that. So there is a significant improvement, but the amplitude noise was before minus 148. Now it is minus 142, so it has increased significantly by the application of amplitude limiting. Seems a little bit odd. And one interesting thing is the correlation between amplitude modulation and phase modulation has disappeared. They are no longer correlated. This means that with a suitable amplitude detector, one could detect the AM noise of this unit, filter it and phase shift it appropriately, and adjust also by the filter the amplitude, to then add a phase modulator that would produce phase modulation that would cancel the phase noise, the part that is correlated. That should give an improvement at all frequencies where there is a correlation. And one could also use that same signal to produce amplitude modulation that would cancel the AM noise also. So there is a scope to make a much better oscillator, at least at wider frequency offsets, by adding such a system. But on the other hand, better to choose another oscillator that doesn't have this kind of problems. I guess there is some unsuitable component, probably a small capacitor, ceramic one, inside the metal box. Ceramic capacitors have to be zero temperature coefficient, NP0 or CG0, I think they are called now. And preferably not the smallest size. All places where there is an RF voltage should have such capacitors in low noise systems. Only big decoupling capacitors can be some other kind of ceramic material. Even better is to use plastic film capacitors. I have inserted a bandpass filter for 10 MHz here. This makes a significant difference. At 7 kHz it's now minus 160 for the phase noise and minus 147.5 for the AM noise. And correlation between AM noise and phase noise is also now very low. Tuning for best performance is for maximum signal now. Before, without the limiter and filters, this is what I had. So compare this with this. AM noise is not degraded significantly anymore. And in particular, if you look here at very low frequencies, this is what I have now. This is without the limiter. So the phase noise at 10-20 Hz or so has become much better. The amplitude limiter no longer degrades the close-range phase noise. It's the same as I had when running without the limiter directly on the card once the capacitor was removed. And at 7 Hz maybe it is a little better even. And the same is for the amplitude noise. I don't see any difference from without the limiter. And the amplitude noise and the phase noise, they are essentially independent. The little noise we see here is just the poor accuracy of the amplitude noise, probably. So there is no correlation between the modulation types anymore. At wide range, the result is ugly. As you can see here, I have been a little bit careless and made some movement that caused a problem, like I did now. It is necessary to not touch any cables or make vibration into the table or so. But nevertheless, the values I can read now at 100 Hz minus 150, 200 Hz minus 152 or maybe 53. That's significantly better than what I had directly on the board. I have changed the parameters to get the result up to 500 Hz more rapidly. The new configuration of the limiter with two filters has moved the noise floor from 144.5 down to minus 150 at 100 Hz. That's from here down to here. And at 200 Hz, before it was 147, that's here. And it's now at minus 152.5. And 400 Hz, it was 148.5. That is about here. And now it's down here. So it's about 5 decibels improvement in this range of a couple of hundred Hertz. The amplitude noise, on the other hand, it was about 150 the whole way from 100 to 400, but now it is 147. So it has degraded, but just a little. And normally one doesn't care about amplitude noise. Not much, at least. Correlation between amplitude and phase noise is 0, very close to 0. So this made a difference. It's interesting, I think, but I don't think it's something that people will use, because it is good enough already just by removing the C14 capacitor for typical purposes, like people wanting to work on 122 gigahertz. This is a good reference oscillator with the capacitor removed.